This is the Washington Bridge that carries I-195 over the Seekonk River in Providence, Rhode Island. Or at least it was the Washington Bridge. You can see that the westbound span is just about completely gone. In July of 2023, that part of the bridge, although marked as being in poor condition, received a passing inspection. 6 months later, the bridge was abruptly closed to traffic because it was in imminent danger of collapse. Now the whole thing has nearly been torn down as part of an emergency replacement project. Rhode Islanders who need to travel between Providence and East Providence have suffered through more than a year of traffic delays from the loss of this important link, and business owners have seen major downturns. If you live in the area, you're probably tired of seeing it in the news, but it hasn't had a lot of coverage outside the state, and I think it's a really fascinating case study in the complexities of designing, building, and taking care of bridges, including some lessons that apply to designing just about anything. I'm Grady, and this is Practical Engineering. The original bridge over the Seekonk River was finished in 1930. Part of that old bridge now serves as a pedestrian crossing and bike link. It's a nice bridge. Concrete and stone multiple arch spans give it a graceful look over the river. In 1959, when I-195 expanded to include this road, it quickly filled with traffic. The old bridge just wasn't big enough, at least according to the standards of the time, so a new bridge to carry the westbound lanes was planned, with the federal government picking up most of the bill. Since the feds were paying, they wanted a simple, inexpensive steel girder bridge, but Rhode Island refused. The state didn't want a plain, stark, utilitarian structure right next to their historic and elegant multi-arch bridge. It took years to come to an agreement, but eventually they met in the middle, with the Federal Bureau of Roads agreeing to include false concrete arch facades between each of the exterior piers, matching the style of the eastbound bridge. But by that time, the field of bridge engineering had shifted. The interstate highway system in the U.S. started in 1956 with the idea of an interconnected freeway system with no at-grade intersections. Every road and rail crossing required grade separation, and that meant we started building a lot of bridges. We're up to around 55,000 today, and that's just on the interstates. With steel in short supply, a new kind of bridge girder was coming into vogue, made from prestressed concrete. In simple, reinforced concrete structures, the rebar is just cast inside. It takes some deflection of the concrete before the steel can take on any of the internal stress within the member. For beams, the amount of deflection needed to develop the strength of the steel often leads to cracks, which eventually lead to corrosion as water reaches the steel. But if you can load up the steel before the beam is put into service, in other words, pre-stress it, you can stiffen the beam, making it less likely to crack under load. I have a whole video going into more detail about pre-stressed concrete if you want to learn more after this. If you've already seen it, then you know there are two main ways to do it. In some structures, the reinforcing steel is tensioned before the concrete's cast. This pre-tensioning is usually done in facilities with specialized equipment that can apply and hold those extreme forces while the concrete cures. Alternatively, you can do it on site by running steel tendons through hollow tubes in the concrete. Once it's cured, jacks are used to stress the tendons, a process called post-tensioning. The engineers for the westbound lanes of the Washington Bridge took advantage of this relatively new construction method, using both post-tension and pre-tension beams. While most of the grade separation bridges on interstate highways were rigidly standardized, this was a bridge unlike practically any other in the United States. It had 18 spans of varying structural types. Except for the navigation span for boats that use steel girders, the rest of the bridge passing over the water used cantilever beams. Rather than having the end of a beam sit on a pier like most beam bridges do, called simply supported, the primary beams in the Washington Bridge were supported at their center, cantilevering out in both directions. The pre-tension drop-in concrete girders were suspended between the cantilever arms. Those cantilever beams were post-tension structural members. 5 steel cables were run in hollow ducts from one end to the other, then tensioned to roughly 200,000 pounds, nearly a meganewton each, and locked off at anchorages on both ends. Then the ducts were filled with grout to bond the strands to the rest of the concrete member and protect them against corrosion. Most of the cantilever beams in the Washington Bridge were balanced, meaning they had roughly the same load on either side. But at the west abutment and navigation span, that wasn't true. You can see that these beams support a drop-in girder on one end, but the steel girders over the navigation span are simply supported on their piers. Since the cantilever beams weren't balanced, designers needed an alternative way to keep them from rotating atop the pier. So, steel rods called tie-downs were installed on each of the unbalanced cantilevers. In December 2023, the now 57-year-old westbound bridge was in the middle of a $64 million construction project to repair damaged concrete, widen the deck for another lane of traffic, and add a new off-ramp, with the goal of extending the bridge's life by 25 years. One of the engineers involved in that project was on-site and noticed something unusual under the navigation span. Some of the tie-down rods on the unbalanced cantilevers were completely broken. The finding was serious, so 3 days later, a more detailed inspection of the structure was carried out, discovering that half of the unbalanced cantilevers at Piers 6 and 7, the piers on either side of the navigation span, were not performing as designed. The Rhode Island Department of Transportation closed the bridge to traffic that day, while the state could investigate the issue and come up with a solution. The closure snarled traffic on a crossing that was already regularly congested. Westbound traffic was eventually rerouted onto the eastbound bridge, with the lanes narrowed to fit more vehicles. The state put up an interactive dashboard where you can look at travel times by route and time of day and view live webcams to try and help travelers and commuters decide how and when to get across the Seekonk River. Still, the closure has had an enormous impact on the Providence area, impacting travel times and economic activity for more than a year now. The state was fully expecting to implement some kind of emergency repair project, essentially a retrofit that would replace the broken tie-downs on the unbalanced cantilevers. The project was designed and the contractor started installing work platforms below the bridge in January 2024. As they got access to the underside of the bridge, things started looking worse. Deteriorating concrete on the beams threatened to complicate the installation of the new tie-downs. So the state decided to do a more detailed investigation. They tested concrete in the beams, used ground-penetrating radar and ultrasound to inspect the tendons inside, and even drilled into the beams to observe the actual condition of the post-tension cables. What they uncovered was a laundry list of serious issues. In addition to the failed tie-down rods, there were major problems with the beams themselves. The concrete was soft and damaged, in part because of freeze-thaw action. Like most concrete from the 1960s, there was no air entrainment in the concrete beams. This requirement in most modern concrete mixes, especially in northern climates, introduces tiny air bubbles that act like cushions to reduce damage when water freezes. Without air, concrete exposed to water and freezing conditions will spall, crack, and deteriorate over time. The post-tensioning system was also in bad condition. The anchorages at the end of the beams were corroded, and voids and soft grout were found within the cable ducts. When the inspectors drilled into the beams to reach one of the cables, they saw that the poor grout job had allowed water inside the duct, corroding the cable itself. Most of the damage was related to the condition and location of the joints in the bridge deck, which allowed water and salty snowmelt to leak down onto the structure below. If you saw my video on the Fern Hollow Bridge collapse in Pittsburgh, it was a similar situation. When the engineers analyzed the strength of the bridge, considering its actual condition, the results weren't good. With no traffic, the beams met the minimum requirements in the bridge code. When the traffic loads were applied, it was a totally different story. The code doesn't allow any tension to occur in a post-tension member, but you can see in the graph that the top of the beam is in tension across a large portion of its length. Worse than that, the engineers found that the beams were in a condition where failure would happen before you could see significant cracking in the concrete. In other words, if the beam was in structural distress, it likely wouldn't be caught during an inspection. There could be no warning before a potential failure. In short, this was not a bridge worth widening. It wasn't even safe to drive on. A big question here is, why didn't any of this get caught in inspections? And that mostly has to do with access. Only some of these tie-downs were visible to inspectors. The rest were embedded in concrete diaphragms that ran laterally between the beams. But it's not clear if any special attention was paid to them given their structural importance in the bridge. Looking through all the past inspection reports, there's very little mention of the tie-down rods at all and only a few pictures of them. The state actually used this photo from the July 2023 inspection, 5 months prior to when it was observed to be broken, to show that this tie-down wasn't broken then, suggesting that maybe a large truck had caused the damage in a single event. But you can clearly see that if it were fractured at the time, that break would be obscured by the pier in the photo. Same thing for this one. The fracture is at the very top of the rod, so it's impossible to see if it was there in July. There's no easy way to know how long this had been an issue. At least for these outside tie rods, you have bare steel, exposed and mostly uncoated, directly beneath a leaky joint in the road deck. This is easy to say in hindsight, but if I'm an inspector and I understand the configuration of this bridge, I'm making sure to put eyes on every one of these visible tie-downs, or at least state very clearly and explicitly that the access wasn't enough to fully document their condition. And it's even worse for the post-tension anchorages in the beams. Those drop-in girders sat essentially flush with the ends of the beams, making it impossible to inspect their condition, let alone perform maintenance or repairs. Seismic retrofits installed in 1996 made access and visibility even tougher. And this is a perfect case study in the risks that hidden elements can pose. If you've ever done a renovation project on an older house, you know exactly how this goes. You start to change a light fixture, and next thing you know, there's a backhoe in your front yard. The bridge widening project uncovered the situation with the tie rods. The repairs to the tie rods revealed issues with the post-tension system and the beams. Investigation into that problem revealed further structural issues, and pretty quickly you have a much bigger problem on your hands than you set out to fix in the first place. You're trying to keep the public informed about what's going on and predict how long the bridge is going to be closed at the same time that the situation is unraveling before your eyes. The engineers looked at a bunch of options to repair all these issues, but the complexity of implementing any fixes just made it infeasible. Just to get to the beams, you'd have to demo the entire road deck and remove the drop-in girders. Since things have shifted, there's no way to know how the load had redistributed, so even taking the deck off would come with risks. Then, with the state of the concrete in the beams, it wasn't a sure bet that they could even support any external strengthening, and even if you did get it repaired, you would still have all the same issues with access and visibility. The report put it in plain words. The options for repair were limited, complex, and did not completely mitigate the identified risks with the structure. So eventually, the state decided to demolish the entire thing and start over. And that's where it stands, or doesn't stand right now. Demolition is well underway, but that's not the end of the mess. The state put out a request for proposals to design and build the replacement project in April 2024 with an aggressive schedule to finish construction by August 2026. Not a single contractor bid on the job, likely due to the difficult schedule and the inherent risks. The state planned to leave the substructure of the bridge, the piers and the piles, intact, giving the replacement contractor the option to reuse it as part of their design. It seems like no one could get comfortable with that idea, and I don't blame them considering how each milestone in this saga has only revealed new bad news about the condition of the bridge. In October, the state decided to just demo the substructure too, adding it to the existing contract. They started a new solicitation process, this time with 2 stages, to try and find a contractor willing to take on this project. The 2 finalists were announced in December, and they expect to award a contract this summer of 2025. But in the midst of just trying to figure out what to do with the bridge, the fight over who's responsible for all this chaos started. In August of 2024, the state filed a lawsuit against 13 companies, including firms that did the bridge inspections, alleging that they should have identified these structural issues earlier. At one point, the Attorney General stopped the demolition work to preserve evidence for the lawsuit, extending the timeline for a month. Then in January, the U.S. Department of Justice disclosed that they're investigating the state of Rhode Island under the False Claims Act, which comes into play when federal funds are misused or fraudulently obtained. The dual legal battles, one against the engineering firms and another potentially implicating the state, turned what was already a logistical and financial nightmare into a high-stakes showdown with millions of dollars and public trust hanging in the balance. Then in February, this video came out showing the demolition contractor dropping huge pieces of the cantilever beams onto the barges below, sparking a workplace safety investigation from OSHA. A fellow YouTube engineer, Casey Jones, has been covering a lot more detailed aspects of the situation if you want to keep up with the story, and I also have to shout out the local journalists who have done some fantastic work to keep the public apprised of the situation where maybe the state has faltered. This saga is far from over, and we're probably going to learn a lot more in the coming months and years. Maybe the inspectors really did neglect their duties to identify major problems. Maybe the state has some issues with its inspection and review program. Probably there's a little bit of both, but also this bridge had some bizarre design decisions that made a lot of these problems inevitable. Putting critical structural elements like tie-downs and post-tension anchorages where they can't be inspected or repaired is essentially like planting a time bomb. We're fortunate it was caught before it blew up. And a lot of those design decisions were driven by a roughly $5 million, adjusted for inflation, battle between Rhode Island and the federal government over the visual appearance of the bridge in 1965. Now it will cost roughly 20 times that just to tear the bridge down, and who knows how much to rebuild. The situation is a mess. It's an embarrassment for the state, a nightmare for the engineers and contractors who have worked on the bridge in the past, and a major problem for all the residents of Rhode Island who depend on this bridge. Every time I talk about failures, I get so much feedback about how bad US infrastructure is. And I don't want to sugarcoat this situation, but I do want to put it in context. This is one of roughly 617,000 bridges in the US, and in some ways, it's a success story. A serious problem was identified before it became a disaster, and the final outcome should be what was needed all along, replacing a bridge that had reached the end of its design life. It's not a bizarre situation that an old bridge was old. It happens all the time, and although sometimes the roadwork is frustrating, we generally understand that structures don't last forever and eventually need to be replaced. But just like engineers design structures to be ductile, to fail with grace and warning, we want and need projects like this to happen in an orderly fashion. We should be able to recognize when replacement is necessary, plan ahead for the project, do a good job informing the public, and execute the job on a timeline that doesn't require panic, chaos, and emergency contracts. And the Washington Bridge is a perfect case study in why that's so important. I am an avid news reader when it comes to stories about infrastructure. I've been following the story of the Washington Bridge for more than a year now until I felt there was enough information to make this video. And I have an update from another video I did when the Francis Scott Key Bridge was hit by a container ship last year. Maryland just unveiled the concept for the replacement. What do you think of the rendering? I knew it was going to be a cable-stayed structure. With news like this, you know a lot of people are going to have things to say. The story was covered by more than 30 sources with a good mix of left, center, and right-leaning sources. Today's sponsor, Ground News, makes it easy to see them all in one place. But more than that, it adds context to help you consider any biases in the reporting. You can see ownership and factuality ratings backed by independent news monitoring organizations at a glance, and a summary of the story based on all the articles with an AI-powered comparison tool. There's a lot to this story, including the tragedy of the construction workers who lost their lives, the lawsuits, and the enormous amount of money the project is going to require. And news sources can slant the importance of those issues one way or another. It can be really frustrating trying to follow the news just to get the facts, especially for controversial subjects like those that involve politics, environmental issues, or ongoing conflicts where there's more motivation to get a particular narrative across. In that way, journalism has a lot of power over us, and Ground News hands some of that power back to you. If you'd like a more transparent media landscape, they're offering a huge discount right now at the link in the description. 40% off the Vantage subscription, which includes unlimited access to all their features. That's ground.news/practical engineering, or just click the link in the description. Thank you for watching, and let me know what you think.